For more physics-related videos, please subscribe. Welcome to the second video in a series on the history of astronomy, in which I'll be covering the Greek Golden Age. In the previous video, I covered astronomy during prehistoric times and the beginnings of modern-day astronomy, ending with Egypt and Mesopotamia at the end of the Bronze Age. At this point, the Middle East and Eastern Mediterranean region was about to be hit by a calamity known as the Bronze Age collapse, in which all civilizations in the area collapsed, some never to return, others managing to survive, such as the Egyptians and the Mesopotamians, and some new civilizations rising out of the ashes of this disaster. One of those civilizations was the Greeks. Now, to be clear, there were Greeks during the Bronze Age as well, but these were Mycenaean Greeks. This is a completely different civilization altogether. These are the Greeks of the Trojan War. The Greeks I'm talking about here are the classical Greeks, the Greeks of Aristotle, Pythagoras, Archimedes, etc. The Greeks you probably think of when you hear of ancient Greece. This new Greek civilization basically had to restart civilization from scratch, as after the Bronze Age collapse, Greece went through a few hundred years of dark ages, meaning they lost the ability to write, so we don't have any historical records of what was going on at that time. When the Greeks rise again, they do so by incorporating the knowledge of their neighbors, primarily the Egyptians and Mesopotamians. In fact, I once heard a quote from a Greek philosopher. I can't remember who it was. I want to say it was Aristotle, but maybe you can tell me in the comments. Everything the Greeks did, they stole from their neighbors, and everything they stole from their neighbors, they improved upon. Something that could probably be said about most civilizations. And one of the things they take from their neighbors is astronomy and mathematics. In particular, they adopt mainly the Babylonian system of astronomy. So many of their constellations are based off of Babylonian constellations, in particular the zodiac. They modify it slightly, and the modern-day Western zodiac is essentially the Greek zodiac. Now, the Greeks make a lot of innovations in the field of astronomy and mathematics, and there's no way I could possibly cover every astronomer and every discovery they made, so I'll just try to hit the major milestones. Starting with the Pythagoreans, they are apparently the first to suggest that the motion of the sky during the day is due to the Earth rotating. To be fair, there are other Greeks at this time also making this suggestion, and they're not all from the Pythagorean school. The Greeks around this time are also the first to suggest that the Earth might be round, at least as far as the historical record shows. Initially, the Greeks do not believe the Earth to be round. Some say it's a flat disk floating on water, which I believe is what the Babylonians said. Some say it was a flat square, which I think the Egyptians also wrote. There's even a suggestion that it was shaped as a drum and we just lived on one of its flat sides. But around this time, we start seeing discussions of possibly the Earth being a sphere. For example, we have some writings from Plato where he has characters discussing the possibility of the Earth being round. However, we have no idea who first came up with this idea or why. You might be thinking, well, why is obvious, the Earth actually is round. This doesn't mean that the Greeks believed this as a result of observation. It's possible they initially suggested the Earth was round based on some sort of ideology or mythological principle. For example, we'll see in a little bit that the Greeks make a lot of claims about the heavens being perfect and requiring perfect geometry, and that they believe the circle to be the most perfect shape, and therefore they try to map everything in the heavens onto circles, or spheres, I should say. So it may be the case that they made the same argument for the Earth, and just happened to be right. If you're finding this video interesting so far, please take a second to like and subscribe, and maybe share it with some friends. It'd help me out a lot. Another possibility is that they got the idea from their neighbors. There is some circumstantial evidence to suggest this. This hypothesis is based on the writings of Herodotus in his famous book, The Histories. In this book, at one point, he talks about the Phoenicians. The Phoenicians were a Canaanite seafaring mercantile people, mainly centered on what is today Lebanon. They were famous for being the greatest sailors of all, even way back into the Bronze Age. They are one of the civilizations that actually survives the Bronze Age. They sailed all over the Mediterranean, setting up trading posts, and eventually those turned into colonies. And they were even known to have sailed out into the Atlantic, all the way up to England and down the western coast of Africa. All of this back in the Bronze Age. They were such great sailors, in fact, that some people have suggested they may have sailed all the way to the Americas. Now, as far as I know, there's absolutely no evidence to support this, but in recent years, a replica of a Phoenician ship was made and was successfully sailed across the Atlantic. This, of course, does not prove the Phoenicians sailed across the Atlantic. What it does show, though, is that they were perfectly capable of sailing in open ocean. So, what does all this have to do with the Earth being round? Well, Herodotus tells us that a Greek pharaoh commissioned some Phoenician sailors to circumnavigate Africa going around clockwise. However, Herodotus doesn't believe this actually happened. And the reason he doesn't believe this is that apparently the Phoenicians claimed that when they were sailing around the bottom of Africa, going westward, the sun appeared to their right, meaning to the north. And Herodotus, who apparently believed the Earth to be flat, said this was a bunch of nonsense. There's no way the sun is going to move to the right. It's going to be in the same place no matter where you are, which would be true on a flat Earth as long as the sun is far away. However, observing the sun to your right as you sailed westward along the bottom of Africa is exactly what you would observe if you actually did this trip. So, some modern day historians have argued this is actually evidence that the trip was successfully completed. The Phoenicians did in fact circumnavigate Africa, some 2,000 years before Vasco da Gama and the Portuguese did it during the Age of Exploration. Now, the argument here is if the Phoenicians sailed around Africa and noticed this positioning of the sun, they would have figured out this implies the Earth is round. But there's actually more to this argument. Given that the Phoenicians were this great maritime civilization capable of sailing in open seas that had been around for a couple thousand years at this point, it's very unlikely they would not have noticed the Earth is round. In fact, I would argue that any maritime civilization would eventually figure this out, mainly because they have to for the purpose of navigation. If you're sailing in open seas, there are only two things to look at: the horizon and the sky. Experienced sailors would notice how objects disappear below the horizon. It literally seems to drop below the horizon. This is a result of the curvature of the Earth. But more importantly, they would have to know how to use the sky for navigation. So they would have noticed that you can use the stars at night to figure out your position, particularly your latitude, by measuring the angle to the North Star. During the day, you can do a similar thing with the noontime sun. So personally, I think it's extremely unlikely the Phoenicians would not have figured out the Earth is round. Does this mean they passed this information on to the Greeks? No, but we do know the Greeks did get a number of things from the Phoenicians. Most famously, the alphabet. In fact, we all got the alphabet from the Phoenicians. So the Phoenicians were writing things down. In fact, they must have been writing a lot of things down because the Greek word for book, biblos, is simply the name of one of the cities in Phoenicia. Ironically, even though the Phoenicians invented the alphabet, we have almost no writing from them because they wrote entirely on perishable materials. Whatever the case may be, by the time we get to the 4th century BC, it seems to be universally accepted that the Earth is round by the Greeks, a fact that would not be disputed until sometime around the year 2000 AD. If you'd like to know more about this unsolved puzzle of how the Greeks figured out the Earth was round, I've linked an article in the description by historian James Hannam. Moving on from the round Earth question, along comes a guy named Aristarchus of Samos. Aristarchus makes the first measurements of the size of the sun and the moon and their distances from Earth. Depending on when you're watching this, I may have a video out, and you can check out his method if you're interested. I will say that his results were wildly off, particularly his results for the sun. This is not because his method was unsound, it was perfectly sound, but it is extremely sensitive to measurement. Very small inaccuracies in your measurements lead to extremely large errors in your results, particularly for the sun. Aristarchus is also the first person we know of to suggest a heliocentric model for the solar system, meaning a model in which everything revolves around the sun. A little after Aristarchus comes a man named Eratosthenes. Eratosthenes makes the first measurements of the size of the Earth. If you'd like to know how he did this, you can check out my video on Eratosthenes' method for measuring the circumference of the Earth. Eratosthenes also develops the first spherical coordinate system that would eventually evolve into the modern-day longitude-latitude system, which he uses for mapping the Earth and the sky. A century later comes a guy who is widely considered to be the greatest Greek astronomer of all. His name was Hipparchus. He's out there every night cataloging the positions of numerous stars and the planets. he makes a number of innovations in the field of astronomy. He develops what's called the stellar magnitude scale. This is a scale for ranking the apparent brightness of stars, how bright stars appear on Earth to the naked eye. This magnitude scale is actually still used sort of today, although it's been modified since the invention of telescopes now that we can observe stars that aren't visible to the naked eye. Hipparchus is also credited with having invented the astrolabe. This is a tool for measuring the position and angles of stars. It becomes the primary astronomer's tool for the next 2,000 years or more. I don't actually know how historically accurate it is that he invented this, but he is generally credited with its invention. Hipparchus is also the first to discover what's called the precession of the equinoxes. This is a term that refers to the wobbling of the Earth's axis. So the Earth rotates on an axis, and that axis doesn't always point in the same direction. It wobbles around like a top over a period of about 26,000 years. Given that a human lifetime is nothing compared to a period of 26,000 years, how did Hipparchus figure this out? Well, he compared his data to much older data, probably from the Egyptians and/or Babylonians. And this shows you the value of taking accurate measurements. He noticed there was a discrepancy between the direction he called north, relative to the sky, and the direction the Babylonians and Egyptians called north. And because he had taken very meticulous data, he was able to rule out the possibility that this discrepancy was a result of error in measurements. The precession of the equinoxes has an interesting consequence on the zodiac. So remember, your zodiac sign is based on what constellation the sun is in when you are born. And you can map out which constellation sits at different times of the year. So you don't actually have to go out and measure the sun. You can say, I was born at the end of July, that makes me a Leo. That would have been true back at the time of the Greeks. Because of the precession of the equinoxes, the sky has slightly shifted over the last 2,000 years or so by about a month. So when you say you were born a Leo, since the sky has shifted, you were actually born a Cancer, meaning when you were born, the sun rose in the constellation of Cancer, and everyone is actually off by about a month. Everyone's true sign is actually the one assigned to the month before them. Hopefully, this doesn't mean you got the wrong tattoo. The Greeks also initiate what may be the most important debate in the history of astronomy, and that is the debate between the geocentric solar system or heliocentric solar system. Does everything revolve around the Earth or the Sun? This debate today is often called the Ptolemaic system versus the Copernican system. But we haven't even gotten to Ptolemy and Copernicus yet. Ptolemy lived in the 2nd century AD, and Copernicus would not be born for almost 2,000 years. It would be better to name this debate after Aristotle versus Aristarchus of Samos. As we saw, Aristarchus is the first to come up with the heliocentric model. But Aristotle did not invent the geocentric model. The geocentric model was the norm, the default position for everyone around the world, long before the Greeks ever came on the scene. So why am I naming it after Aristotle? Well, Aristotle championed the geocentric model, and everyone considered him to be such a smart guy that basically everyone went along with him. So why did Aristotle support the geocentric model? Well, he argued the Earth could not be moving. He even believed it couldn't be spinning, even though we saw a number of earlier Greeks argued it was spinning. His argument was if the Earth were spinning, there would be such high winds we would all be blown off of its surface. Now, before you laugh at Aristotle here, the world doesn't know about inertia and Newton's laws of physics yet. We're well before that. So he doesn't realize, well, actually, the atmosphere, the air, is spinning with the Earth. That's why we're not blown off. But actually, ironically, he's kind of right. The spinning of the Earth does cause high winds. It is what's responsible for these cyclone-shaped patterns of large storms. If the Earth wasn't spinning, we would not get these cyclone-shaped wind patterns. Now, you'll recall I mentioned that the Greeks make a lot of arguments about the natural world based off of mathematical perfection, and Aristotle is no exception. Despite being a smart guy, almost every claim he made about the natural world turned out to be false. For example, he claims that the moon, being part of the heavens, must be a perfect unblemished sphere. Well, I'm sure you'll agree with him that the moon is a sphere, but unblemished, that's a rather strange claim. All he had to really do was look at the moon to realize it's blemished, and it's blemished in a shape that kind of looks like a rabbit. And actually, there were Greeks before him arguing that the moon had mountains and maybe even had civilizations living on it. This concept of the heavens being made of perfect spheres is the basis of his geocentric model. In his model, each planet, the sun and the moon, are moving along a spherical shell in perfect uniform motion. So they go around in perfect circles at a constant speed. The only shell that is not rotating is the outer shell on which the fixed stars are essentially glued. You may be laughing here at poor Aristotle because of his idea of mathematical purity and perfect geometry, but many modern-day physicists and academics still fall for this mathematical beauty flawed logic, particularly very mathematically minded theorists. They become so impressed by the beauty of the math that they interpret this as evidence of reality. The most famous example of this is string theory, which has zero experimental evidence supporting it, but the math is so beautiful and symmetric and perfect that it has convinced many physicists that the world must work this way. Another example is the theory of supersymmetry, if you've heard of that, also based on ideas of perfect symmetry in the math, a theory that people once thought for sure would be proven experimentally, but that theory too has so far failed to be supported by experimental evidence. So don't go too hard on Aristotle. Even the smartest physicists in the world today often fall for this flawed logic. Now, how about Aristarchus' heliocentric model? Well, it's basically the same model. All the planets are moving in uniform motion on perfect spheres, only instead of the Earth at the center, we have the Sun at the center. And the Moon is going around the Earth, which itself is going around the Sun. Aristarchus does make one further observation. He is the first person that I know of to have claimed that the stars and the sun are the same type of object, that the sun is just a nearby star. As a result, he argues, the stars must be much further away than everyone else thinks. This guy is actually pretty clever. So we have this debate between the geocentric and heliocentric model, but everyone's pretty much going with Aristotle based off of his philosophical arguments. However, the geocentric model very quickly runs into a problem, and that is what we call retrograde motion. All the planets, if you map their position night after night, appear to move in the same direction, except once in a while, they will turn around and move in the quote-unquote wrong direction for a little bit before turning back around and going back in the correct direction. This retrograde motion is often associated with evil omens, and the geocentric model cannot explain this observation. The heliocentric model, however, has no problems explaining this. This is simply a result of planets passing one another in their orbits. So let's say Earth is these blue dots. As you pass an outer planet, it could be an inner planet, it doesn't matter. So let's say this outer planet is Mars. As you pass Mars in your orbit, it appears to you that Mars moves backwards. Just as when you pass a car on the highway, it appears to you like it's moving backwards. So you would think this basically kills the geocentric model. But along comes a guy named Apollonius of Perga who says, not so fast, I have a solution for this. He makes a modification to the geocentric model, which he calls the epicycle. Apollonius says, actually the planets don't go around the Earth, they go around a smaller circle whose center is going around the Earth. And because the planets are moving around this smaller circle, called the epicycle, occasionally they appear to move backwards. Now, why are we bothering complicating this model with this weird epicycle business? Why don't we just admit the heliocentric model must be correct? Well, actually, the heliocentric model has epicycles too, in the case of the moon. The moon goes around a smaller circle whose center is going around the sun. The only difference is, in the case of the moon, there's actually an object at the center of the epicycle. That might seem reasonable to you, but remember, back then, they don't know that the orbital motion is the result of gravitational attraction. As far as they're concerned, the planets move around because the gods said so, and they base it off of geometric perfection. So Apollonius saves the geocentric model with the invention of the epicycle. But then Hipparchus comes along with his star charts and his meticulous data and his catalogs of astronomical observations, and notices something funny. The planets seem to move a little bit faster during the winter than during the summer. But this violates the principle of perfect uniform motion. So he makes another modification called the deferent. He says, yes, everything's going around the Earth, but the Earth is not actually at the center of this larger circle on which travels the epicycle. It's slightly offset. As a result, when a planet is on the far side of the Earth, it appears to move a little bit slower, meaning its angular displacement is slower. And when it's on the near side of the Earth, it moves by faster. So all is good. We still have perfect uniform motion. We just have this offsetting of the Earth's position. Once again, the geocentric model has been rescued. A few hundred years go by, and along comes a guy named Ptolemy. Ptolemy is called a Greek, but he actually lived in Egypt when it was part of the Roman Empire. Probably he should be called Egyptian or Roman, but he had a Greek name, which I don't even know if it was his real name, and he wrote in Greek. Does that make him Greek? I'll let you decide, but that would be kind of like calling Martin Luther King English. Ptolemy, who's living a few hundred years after Hipparchus, starts noticing slight problems in Hipparchus's model. And he makes one more modification to the geocentric model. He invents the equant. He notices that Hipparchus's deferent doesn't perfectly account for this varying apparent speed of the planets throughout the seasons. So he says, well, actually, the center of this epicycle is not moving at a constant rate. It's going a little bit slower when it's on the far side of the Earth than when it's on the near side of the Earth. But you say, you've just violated perfect uniform motion. Aha, says Ptolemy. No, I haven't. It's true that the motion is not perfect and uniform, but were you to stand at this hypothetical point called the equant, an observer sitting there would observe perfect uniform motion. Meaning, from that person's point of view, the center of this epicycle would go around at a fixed rate. And therefore, he argues, perfect uniform motion has not been violated. As time goes on, we're getting a lot of bending over backwards to make sure the data matches these ideological presuppositions. And in fact, my understanding is there's evidence that Ptolemy may have even fudged the numbers a little bit to force the data to fit his model. Now, Ptolemy is the last of the great Greek or Greco-Roman astronomers, and he quantifies his work in a very famous book called the Mathematicae Syntaxis, known today as the Almagest. How on earth did we get from Mathematicae Syntaxis to the name Almagest? Well, the book quickly acquired the nickname Syntaxis Majesti, meaning the great syntax, and then it was translated into Arabic, and the Arabs called it Al-Majesti, al being the Arabic word for the. The Arabic version was then translated into Latin by Western European Christians much later on, who further garbled the Arabic garbling of Greek into Almagest. So this gives us a preview that one of the next big civilizations in the history of astronomy are the Arabs, but we're not quite there yet. As far as this geocentric, heliocentric debate, pretty much everyone's going with the geocentric model, but I should point out, at this point, the geocentric model and the heliocentric model are equally good or equally poor at predicting the position of the planets. This debate would not be fully resolved until Newton's universal law of gravitation, but we've got a long ways to go before we get to Isaac Newton. Now that we've finished with the Greeks, there are other civilizations who are practicing astronomy at the same time, and one of those is ancient China, which we will take a look at in the next video. So if you've enjoyed this video, and if you're enjoying this series, be sure to like and subscribe, and hit the bell to be notified for the release of future physics and astronomy videos. Thanks for watching, and hopefully I'll see you in the next one.